Okay, so atomic radius. That is the most important thing of all of the trends. If you understand the size of the atom, you will understand a lot of what is happening as we move forward in here. So I had written on your sheet half the distance between the two nuclei of two like atoms, and that's great. But the biggest deal for me is I have those D's and those I's on there. What I would do is make potentially little phrases or notes so you understand this. And what people don't understand is the first one I said. So I'm going to talk about the second one first. That's pretty straightforward. If you look in the lower left of your note sheet, I have a nice little diagram, which is up here, right? You can visually see the atoms. They get bigger as they move down. The reason why, you're gaining energy levels. If you'd like to, you can write that next to that I, if you'd like. Like the reason why they're bigger in the lower left is you're increasing energy levels, bigger energy levels. Okay, again, it's your call how much you want to make this, but that part people usually get. As I move down each period or each row, I'm gaining energy levels. What people don't continually understand, and this will make or break your test, is moving across. Why are these getting smaller? We are gaining electrons, we are gaining protons. Why the heck would it get smaller? We're adding things, they should get bigger. And the reason is what I wrote right here. And again, if you don't feel like there's enough room on the sheet, you can always use a note or a loose leaf as well. But there's nuclear charge. It's the money word. Nuclear charge is the size of my nucleus. We're not talking about North Korea or anything like that when I say nuclear charge. I'm talking about the size of my nucleus, so I'm gaining protons. Right? Protons are like 1,000 times heavier than an electron. So even though protons and electrons attract each other, the protons are going to suck in those electrons as I continually add more and more protons. So as you move across the periodic table, the atomic radius gets smaller and smaller because the nucleus is pulling that electron out. If you're like, so what? Big deal. I don't really care. The attraction, keep it real straight today. Everything I'm talking about is the nucleus attracting and holding on to an electron. The better I can hold on to an electron, that means a lot of things for me. All right, so that's going to be based off of everything we're going to be working on. Can you make your notes or however you'd like? So energy levels going down, nuclear charge going across. And that word nuclear charge can cover a lot of things as we explain some stuff later in the hour today. So ionization energy, I'm jumping right to that one. By the way, shielding effect, I think I have it on there. That's just a fancy thing to talk about how the fact that as you move down the table, you're gaining more inner electrons. So when I'm reaching for those outer electrons, they're shielded, and those outer electrons aren't as attractive to the cell. So shielding effect just helps it. But ionization energy is the energy to remove an electron. I think I have that already written on there, I believe. Is that correct? Yes. You might want to underline the word removing. It's in the upper right on your sheet. So let's talk about why. So it decreases down. And this is why. Again, you can paraphrase however you want. And I do have an image in the lower right on this one. It shows kind of a 3D kind of way of going about this. But if I can remove an electron, if I'm holding Ben's Pepsi right here, the further it is away, the easier it is to remove, right? If I'm holding it really close, that's going to be really hard to get it out of my kung fu grip, right? When you're playing football, you don't get taught to hold it like, hey, just run down the field and hold it like this. You're secure. You would tuck it away. If you're holding your aunt's old vase, because if it's really fancy, you wouldn't use your aunt's vase. Your aunt's vase, right? It's expensive. So you wouldn't carry it like this down the street if it was really expensive and worth a lot. You would really make sure you had it. So if it's further away, it's easier to remove. This I would make sure I make a note on though. If it's easy to remove, so Max wants to remove from me. If it's easy, it's going to take a lot or a little energy. It's going to take a little bit of energy of his, right? So that's the key word here, is it decreases. Not because, oh, we can remove an electron, so it's easier, so it increases, we can remove it easier. It's about the energy. So it's less energy, easier to remove. That might just be a phrase you want to write. Less energy, easier to remove. Because what happens is you guys will flip that. So when you're just looking through it, it'd be good just for you to mentally see that. So that's why it decreases going down. So obviously, it's the opposite going across. Going to the upper right, it increases. Why? It's getting smaller. I'm bringing that object in closer and closer to that nucleus. That attraction is going to be stronger, so it's going to be more difficult to remove, so you would need more energy to remove it. So closer, or more energy, more difficult. remove, something like that, okay? So your job is to know the more in the upper right, the more difficult it is to remove. This stuff should make sense. These don't lose electrons, they gain electrons, right? What's the charge for Cl? If I say what ionic charge, you say Cl minus. Why minus? Because it gained an electron. These gain electrons. What's the charge on Na? Na plus 1. They lose them. They lose them a lot easier. I would throw sodium in water, but if it flew right now, we'll do it tomorrow. If it flew on the carpet, Lee would be in a lot of trouble. We would be back in school for that. So, do it. I've been telling you, Tyler. Here's another picture we're going to use a lot for the rest of the hour today. This is really important. Do I have that on the back of it? Okay. Chemistry. So this is probably, in my opinion, the most important single diagram on my notes today. And I don't want you to dirty this up too much, but I want to just point this out first off. So what are all those top ones? Those are my noble gases, right? What it's showing is that those are the most difficult to remove. That should make sense. We have achieved a full octets. I'm going to start getting this out of your system right now. Nothing wants to be stable. Nothing wants to lose or gain something. Nothing wants, no element wants something for their birthday because they don't have feelings. So if you use the word want, you are going to get torched. It wants to lose an electron. It wants to gain an electron. It wants to be stable. It doesn't want a pony or a car or a new phone. So let's talk about this first. These are more difficult to remove. You may just, if you're feeling like you might dirty it up, we're going to be taking a lot of notes on this one later. So I'm just trying to show you that as you move down, though, why is it getting less difficult to remove? They're getting larger. And that's something that you might want to talk about. Why is that? What's the point of that? The outer electron is getting further from my nucleus. I'm going to keep saying the exact same thing. Nucleus, outer electron. This can be difficult or hard if you just keep the eye on the prize, where it's the attraction from the center to the outer electron. About all these things. That's all this is. So if you want to talk about something being removed, hey, why is this easier removed? It's not being as strongly attracted. Why is this difficult to remove? It's strong. It's being held tighter. The nuclear charge is bigger, or the electron's closer. It's all it is. Why do they steal that from you? Because I'm really weak. That I'm not strong. Why couldn't they take it from that huge bouncer? Because he's huge and scary and strong. So he was holding on to it tighter. Like it still goes back to who can hold on to something and who can't. These are my what? What are all these? Those are my alkali metals. That should make sense that those are the easiest to remove. Why? Because you just reset and you added a new energy level, so the electron just instantly got further away. And then as you move across the table, it slowly starts to shrink. If you were in my classes last year when I taught this, parts of it, I talked about my Thanksgiving tradition of slurping the jello. Right? Anybody remember? So I invite you all this Thanksgiving. If you have jello, some of you I found out that not everybody on Thanksgiving actually has jello. We have a bowl of jello, not for each person, but we have one bowl. Now my aunt, she puts in bananas and grapes in it and ruins it. Like, I don't like that. I just like pure jello. And then the schlurker, which right now is me, because if I have one more bad year of slurking, I'm out. But you put the spoon on the side and you slurk the jello. And that's how you start Thanksgiving, with the slurk the jello. So I invite you to slurk the jello. You may like it. All right. Well, all right, so I am not going through every single, I'm not going through every other trend. If you want to just look on the front, though, I want to just talk about one more. So just go back to the front. Electron affinity. So notice it has the same D and I, but can you just underline adding for that? Make sure it's adding for electron affinity, underline adding. So let's just, I'd like you to make a little note to the left of the D and the I. So why is it easier, or why does it increase to add or decrease to add? The reason why on this side, this is an I, it increases adding electrons, so it's easier to add an electron. Why do you think? Because the outer part of the, don't write this yet, but the outer part of that atom is just closer. It slurped all the way across it. It got really small. So that the outside of that atom is just closer to the nucleus. So the nuclear charge is bigger, and the outer electrons are closer, so it's easier to be attracted to that nucleus. Why is it difficult to add electrons on this side? Because they're so much further away with a much smaller nuclear charge. So the attraction is just stronger on this side. The attraction from the nucleus to the outer electron is stronger, so it's easier to add an electron. I mean, that's like if you were going to throw me something. If I caught it in close, it's easier to catch. I got to Odell Beckham this thing because it's really far away. So it's harder to bring that in. So the further something is away, the more difficult it is to add. So that's why it decreases. All right, so let's talk about a couple scenarios here. On the back, I made that image small on purpose. I want to talk about some different exceptions. This is definitely the difference between AP and general right now. Is that in general, we just say, hey, it increases going across, or it decreases going across, and done. So, for example, here, as I move across here, we say that to remove an electron, it's getting smaller and smaller and smaller, so it's getting more and more difficult. It takes more and more energy to remove it. Okay? But what this shows is that it's taking more energy, less energy, more energy, more energy. What up with that? It should continually get harder to do that because oxygen has a bigger nuclear charge. Okay, so before I show you, we're going to cover a little thing. So kind of be doing this, maximize your space. Like that first example, maybe another one, maybe another one, maybe another one. We're going to talk, I think, about 4 things off of this one chart. Okay, I don't know that off the top of my head exactly. It might be 5. You have 2 things to talk about, and this is where you have to keep it straight. We're going to be really on Monday, we're going to talk about this again, and I'm going to keep pounding the drum on this. You can either talk about nuclear charge, or you can talk about the distance that the electrons are at. But if you talk about that something's easy to remove, you can't talk about a bigger nuclear charge. So in this case, what students will do is they'll say, well, it's easier or more difficult to remove. They'll say something with oxygen versus nitrogen, and then they'll bring up nuclear charge. And your debate is totally wrong. You are on the opposite end of that because oxygen has 1 more proton. So in theory, it should be able to hold on to electrons more. If you're looking at this right now and going, I don't even know what I'm looking at. What are you talking about? The fact that this dips down is saying that the oxygen's next outer electron is easier to remove than nitrogen. But oxygen has a bigger nuclear charge, so shouldn't it be holding it in more? So when you're stuck or don't understand why, you got to look at where the electrons are. So what I have right here is the final part of both electrons. So this is nitrogen, this is oxygen. Okay? Now I don't have, I'm just going to paraphrase, so we can just talk about this. But I would draw that on the side. Like this is important. Can't see it there, it looks better here. This projector is so much nicer than that. So this right here, my friends, this is the electron that's being removed in nitrogen. This is the electron that's being removed in oxygen. How do you know that? The last electron. It's always the last one that you would place. And if you think that would be the last electron that you draw, we're not doing these right. Right? We go through. And I didn't do that in the video. As I'm just saying this now, I realize that. I hope you watch that. Trevor, were you not here yesterday? Were you here yesterday? You're the only one that didn't pick up all your homework. I still have some, but I tried to get out. I hope if you recycled that, that was a bad move. You needed to organize that eventually, so go find it. So, please, let's write what we're going to talk about. This one clearly is being easier to remove. So you can't say, well, it's easier to remove because oxygen has a bigger nuclear charge. But you can't talk about the fact that it might be larger because you don't know that for a fact. So, what's the charge of an electron? It is negative, correct? You have 2 negatives packed in one little orbital. So these are some very specific situations that you might be asked. So you have to study these. There is a natural repulsion that is happening right here. And I would write almost literally that exact phrase. There's a natural repulsion. So it's easier to remove that electron due to the electrons being paired in the same orbital here. That is the exact reason why it's easier to remove that one electron. That you pair them all up. The other one, they're all separated, so they're all apart. But you have this natural repulsion. That repulsion's having them being pushed away. So they're almost being forced into an orbital together. So it's easy to remove. Now, you're going to run into situations that I may not have taught about, but they'll relate to this. So you just have to take a breath and go, okay. So it's telling me that this is easier to remove. Okay, let me go through the things that I've learned about why it would be more difficult or easier to remove. Well, it can't be the nucleus because this one's bigger. So it's not holding it in tighter and it's not pushing it away. So there's something else. Okay, well, there's electrons by with another one. There's that repulsion. They're paired up. Okay? So that's it. That's all you have to say. So that's how you remove it. Okay? Let's talk about another one. There's all sorts of different scenarios that I want to talk about. Let's talk about the BE and the B. So let's talk about where these are. So this one is right here, bless you. And then this one goes here. What's happening to B? What happened from here to here with my electrons before I show it? But where's the last one in B? Where's that one going to be? It's going to be in a P. Isn't that going to be in a new sublevel? Okay, so that's BE. That's B. This is really important. What did I say? The biggest two things you can talk about. So the first one I did is actually really, really specific. Like it's like the electrons are there versus here. Like I have to talk about it exactly that way. Every sublevel, you guys, is technically a little further away. So I have an S, 1S, 2S, 2P, 3S, 3P, 4S, 3D. Like they're not like 2S, 2P, 3S, 3P, 3D. They're not all at the same level. Every sublevel is a little further away. So here are the two reasons why, bless you, this one is easier to remove. Two things. One, the P sublevel is further from the nucleus. If you want to be the gold star extra bonus student, it also, the S sublevel adds one more layer of shielding. And every time you add shielding, I mean, think about it. If I'm holding something and someone starts to hit my arm, it's harder to hold on to it. Now two people hit my arm. Now three, it's blocking and breaking down that attraction from my nucleus to the outer electron. So if there's one more thing in the way, that attraction is getting a little less. So those are two reasons. The big one, the P sublevel is further away. Remember, it's either how big the nucleus is, how far away the electrons are, and then the discussion of how tight or loosely it's being held because of those things. Okay? So that's that reason. Now, I'm giving you stuff because you're going to have to practice 4 different problems in a minute. What else do I have? Huh? Okay, I added something. I don't think, is that written? It must not be written. No. So figure out where that is under ZN. So you got to write it in there. Some of these might be similar. Some of them might be different. So let's talk about that one. So you got to look at the table. So check this out. I have the ZN and then I have the GA, right? So what is ZN? If I said ZN and you wanted to end on ZN, can you tell me what that is? Like, is that a 2S2? What is that? That's what, Ben? 3D10. These are one behind. Very good. So this one is the GA. I'm trying to show it based on where they are. This one's the ZN. I'll let you write that down for a second. That's just kind of the ending. That's not everything. Okay, notice what I'm doing. So I'd write this on the right side maybe. We don't have many more examples. Or below it, something like that. Fit it wherever it's here. I think you can already tell me. Why is that easy to remove? It's not nuclear charge because GA has an extra proton, so it should be able to hold it tighter. So if it's not about the charge, then what it is, it's about distance or about something else, or maybe shielding. And I've already given it away. I have another electron in a further sublevel, right? That sublevel's further from the nucleus. And then if you need to ever end that in an actual sentence, which means I have a weaker attraction, right? But you just need to say some phrases for right now. What else have I gained? An extra layer of shielding. This is actually a lot of shielding. See how big that drop is? If I had to talk about why that was such a great increase, you just gained, please focus in and make sure you hear this. I just gained 10 extra electrons that are now deflecting if my nucleus is down here, that attraction. Here, these aren't in the way. My nucleus is right here. I'm just trying to get rid of that remove that electron, so that attraction is maybe from here to here with other things in the way. I just added a huge amount of electrons in my way that will weaken my nuclear electron attraction. Okay, so I gained a big, if I asked, discuss the huge difference compared to other ones. Because I gained an entire 10 electrons in my shield. If that makes sense. Like, it's in the way. Keep it straight. This doesn't have to be all about thinking in terms of chemistry. It's about ideas of attraction and if something's in the way of that grasp. I think I have one more. Yep. What are your gas asks something simple? Hey, that noble gas and that noble gas. Now, you don't have to necessarily draw it like this. You could just say a phrase for now. What have I basically gained? What's the reason for this one? I know it sounds like I'm repeating myself, but I'm giving you different scenarios that you could use the same kinds of explanation. So what have I done? I've gained an entire energy level, right? So my electrons are further away and there's more shielding. Well, I keep writing that, yes? There's different kinds. This one, they're both full. You don't talk about, well, they're both full. They're both stable. That's great. You know, they don't know they're stable. So I'm like, oh, well, we're stable. We're so much better. Just a second. I just want to see. Oh, shoot. Ha! There was one of mine. So if you're drawing all that, that's way too much. Like, you could just write 3p versus 4p or something. Or, sorry, 2p versus 3p. It's further away. 2p6 versus 3p6. I want to get to the last one. Right there. So I hope this one also makes some sense. And this one you could talk about two different things again. And if you always feel like you're repeating yourself, they won't ask every one of these. But just another good situation. Again, don't have to go crazy on your notes here. Nuclear charge is not in the debate. Nuclear charge is actually not usually on exceptions or things that I want to point out. Nuclear charge is kind of straightforward. Hey, I moved across the table. Why is it more difficult to remove it? I have a larger nuclear charge, so the electrons are more attracted to my center. This one, what have I done is I've gained an extra level, right? The electron is further away one more time. But again, wanting just to have you see some different scenarios. The biggest two I thought today already were these though, because those actually don't follow like the normal pattern as much, and those are a little more unique. Seeing and knowing that you can talk about, wait, I can talk about a sublevel being in the same energy level being further away. Yeah, you can, because that's actually what's happening. So what I'd like, on a sheet, you can work with someone else. I would actually write down and paraphrase these questions. What I'd like right now is, first off, for surely, you're going to start on a certain question, and then if you have time to work on the other ones, you definitely can. For the first row, I want you to work on letter A, second row, letter B, third row, letter C, fourth row, letter D, okay? I'm going to ask somebody, and I'm just going to pick on you. I'm not asking for a volunteer. Is why, what's the reason? Okay? If you have time to work on another one, you definitely can. So if you want to work with some other people, you can. But I want to know, for the first row, potassium has, I'm telling you a statement. Potassium has a lower first ionization energy than lithium. Explain why. B, the atomic radius of N3 minus is larger than that of O2 minus. Why? C, a calcium atom is larger than a zinc atom. Why? And last, boron has a lower first ionization energy than beryllium. And maybe you're like, man, he might have given us something close to this. I want to hear the actual 2 to 3 sentence explanation. So some of the words you're going to use: nuclear charge, maybe energy level, maybe distance, shielding, okay, weaker or stronger attraction, but never ever giving it a personality. So give it a shot. Caitlin, potassium has a lower first ionization energy than lithium. Why?
Potassium has more shielding, and that makes it have less attractions to outer atoms.
Good. So it has more shielding. Anything? Anybody else on the front panel want to just add? Nothing that she said was wrong. There's one other big thing though that I want to hear, and you potentially might not get all the points. What else about that electron, the potassium? Luke?
It's further away.
It's further away. Okay, so you can paraphrase this. So the other rows, please let me just read it out loud once. So it says electron, potassium's valence. Good use of a word. You're talking about the outer electron, right? So valence is a good use, a good vocab word to be applying. It's 4s1 while lithium's 2s1. Sometimes it's important. I just wanted you to see an official answer. Sometimes it's important to just literally state the situation. It's not a bad idea. So maybe for this first one, if you want to just kind of copy this first one down all the way just so you see a really good example. I'm also taping this so you can watch this later. But you state the situation. And then potassium's electron is shielded by more electrons than lithium and is therefore more easily removed at lower energy. You know, Kaylin, I didn't actually write it as further, but it was kind of stated here. The big one is, though, shielding, and then to me, though, it is further away. So it has a weaker attraction. Okay, so again, there's not one right way to do this. There are wrong ways to do this, but there are different styles that you can definitely do. But sometimes stating the situation, because you got to talk about both. I'll tell you that. You can't just be like, well, this one's further. Well, where's the other one? Like, as we continue getting into this, I mean, we're just talking about it, but an official answer, if you want to cover your bases and make sure that you can't get hit by a technicality, you've discussed both things, even if maybe, I was thinking about it, I didn't do a good job talking about that. All right, second row, I kind of threw you a curveball. We didn't really talk about this yet, but hopefully you can kind of figure this out. The ionic radius of N3 minus is larger than that of O2 minus. And what do you have? Give it a shot. You have something? Okay. Courtney, what do you have? Just read what you have.
The ionic radius of N3 minus is larger because it has another energy level because of the extra electrons.
Okay, we're half right. We do have extra electrons. Anybody want to add anything? So, very unfair to row 2, but I want to see what people could do before I said it. Everybody on your sheets, look at your note sheet on the bottom left. So there should be a circle, bottom left in the back. See those atoms? And it's called isoelectronic. See that? If you notice, I'm going to do it right here. Notice the middle one's Ne. And I do O and F. Check this out. If I add 2 electrons, doesn't it have the same number of electrons as Ne then, right? And then F minus is 10, and Na plus is 10, and Mg2 plus is 10. Isoelectronic means that you have the same number of electrons. It's okay. Like, that's what happens with all charges. But what happens is you have greater or smaller nuclear charge. So the very fact that I'm adding electrons here on nitrogen, it has a smaller nuclear charge than oxygen. The nuclear charge, don't write all this, pulls in the electrons greater. So nitrogen has a smaller nuclear charge than oxygen, so oxygen has the ability to pull the electron cloud in tighter. Also, oxygen only gained 2 electrons, so a cloud is literally a number of electrons, right? Don't you have more electrons? So the thing that was said wrong, you don't have more energy levels. You have the same amount of energy levels. You're all at 2 energy levels. It's about the nuclear charge. Why is Mg2 plus on your sheet, you guys, if you look back at the image, why is that one the smallest? Because it has the biggest nuclear charge. Sucks in the cloud. Every one of those has the same number of clouds. Same number of electrons in the cloud. It's just based on the nuclear charge. Does that make any sense? The cloud all has the same number of electrons. You might be gaining more or less, but the nuclear charge, I'm not even reading all this. The greater the nuclear charge, the more the electrons are going to be pulled in. Okay? So you should be paraphrasing. I see everybody reading that, but I'm trying to tell you what you should write. All right. Katie, what do you got? A calcium atom is larger than a zinc atom.
Okay. You see it has less protons because it has less protons. And then since zinc has more protons, there's more of a pull to it and there's more electrons.
So whenever we say protons from this point forward, we're going to say nuclear charge. You're right, though. Perfect. Don't write this down verbatim. If you said, though, zinc has a greater nuclear charge. Great. you need to explain that though. You need to go further with that. So calcium is larger because it doesn't have as big of a nuclear charge, so the electrons aren't pulled in as tight, right? Zinc, or then you could say zinc. What I would do is actually say this. Calcium has 20 protons, while zinc has 30. Zinc has a greater nuclear charge than calcium, so those electrons would be pulled in tighter, causing zinc to be smaller and calcium to be larger. Something like that. You just got to find, what are they talking about? Are they talking about the distance, or are they talking about the nuclear charge? I know we're right about that time, but I want to get the last one. Boron has a lower first ionization energy than beryllium. Sophia? And I know we talked about this a little bit. If Sophia wanted the full points, you would have wanted to establish where it was exactly. And that's something I didn't say beforehand. So when we practice this again, you guys want to literally say the electron in boron is in 2p, while the valence electron in Be is in 2s. The 2p is further away, and there's more shielding, so it's easier to remove in B than Be. And that was actually the situation we just did on your note sheet. We already had that one. Okay? I know that I threw those out there at the ending, but you have one thing to do today, I believe, the review, right? Radiant energy review, that should be done. You can put it up on the front table if you like.